So, yeah, I'm William, and I'm going to present a work done with Ali Neshati and Pourang Irani from the University of Manitoba and Xiangshi from the Kochi University of Technology in Japan. And this work is about an analytic model for time-efficient personal hierarchies. So first, what are hierarchies? They are everywhere in our lives. They can have a static content, like software menus, or an audio menu, like press 1 to access this service, for instance. Or they can have a dynamic content, like your own file folders or application launchers on your smartphone. And we focus on the dynamic content because it is still the user's preferred information retrieval method, and the selection time is one of the critical factors of this retrieval method, and it fits the storing and growing of information content trend. Let's consider an example just to motivate this work. Let's assume I have this movie hierarchy, and I add new comedy movies. I guess the average selection time of this folder increased, but I don't know by how much. And I want to reorganize these movies anyway, so I could create a dark humor subfolder. I can also think about creating a satire subfolder along with the dark humor, and I can also think about two other ones like absurd and cringe. And I am fine with all these options I can think of, but I don't know which one could actually lead to a fast selection time. And our goal is to actually help users decide which option they can envision is also time efficient. And for that, we need to be able to predict the average selection time of these options. So we build on previous work focusing on hierarchies, but with static content, and we can distinguish between algorithmic and analytic approaches. For algorithmic approaches, one example is this recursive methods. So designers can provide a hierarchy structure, and the system can then explore new structure by deleting sublevels, and the new hierarchies are then respecting the semantic constraints. Another example is menu optimizer. So it includes an optimizer to help designers creating linear software menus. And it uses a multi-objective optimization approach to maximize user performances by considering frequency and grouping of labels, for instance, to maximize users' expectations by considering also other linear menus, and to minimize designer edits. And this tool also includes several features to interact with the optimizer and to visualize the results. So these are solutions, but for static menu, known in advance, and for knowledgeable designers. For the analytic approach, I won't describe every model, but basically the selection time is defined as a function of some parameters, and then this function is analyzed to find the best solution. So for instance, previous work considered as parameters the total number of items in the hierarchy, the number of items per group, number of groups, the delay to search an item, the delay to select it. And they did find that the best solution was to get between 4 and 8 items per group. And by including the learnability as a factor, the best solution was found to be between 16 and 78 items per group. And by including the item selection frequency as a factor, previous work extended the result from completely balanced hierarchies to homogeneous hierarchies. So previous analytic approaches allow to find the optimal global solution, but for specific hierarchy types, and they have not been evaluated. So compared to previous work, we focus on hierarchies with dynamic content and without presupposed knowledge from end users, such as the frequency and the grouping. And we want to provide a range of solutions for flexibility, while still preserving the existing structure to not interfere with users' habits. And we also want to not constrain the hierarchy to a specific type. And finally, we also want to validate our approach. So for our model now, let's consider this hierarchy represented with a tree, and we define 3 delays. D1, the delay to look for a node, D2 is the delay to select a node, and D3 is the delay to go to the next level. And so the average selection time of these nodes at level j is given by the standard average selection time. But now, if we reorganize these nodes with level j and j plus 1, this is a new average selection time. So without going into the details, this model considers the time to look for a node, the time to select it, the time to go to the next level, and the time to look for and select the children. So to work with this model, we do one simplification. We consider the number of children constant. So what does it mean for the overall hierarchy type? Not much, because since this approximation is per group, a user can still create groupings with different numbers of children between groups. Here, 3 for the green group and 2 for the yellow group. But of course, even in one group, it might not be possible to have the same numbers of children in each subgroup. So in case of unbalanced hierarchies, we can simply apply a heuristic based on the number of nodes. Let's consider this group of 2 and 3 nodes, and with a top-to-bottom exploration. Then we should place the bigger group, or the group accessed more often, at the top of the hierarchy. So our model depends on 6 parameters, 3 delays, and 3 hierarchy structures parameters. And delays can be determined via previous work. I will give the example of the search decision and pointing model with linear layouts. And then D1 is the visual search time for novices, the decision time for experts. D2 is a well-known pointing time given by Fitts law, and D3 corresponds to the steering time to move the cursor to the next level. So now we can simply focus on the structure parameters. I invite you to read the paper for the mathematical details, but what we can do is, of course, find the best solution. We can validate a new structure. The system could tell users if a modification will be more time efficient, and if not, when this would be the case. Because creating a hierarchy is flexible, so basically user could revise their grouping if they want to. The system can also recommend a range of children number. If I create a new subfolder, the system can tell me that it would be best to transfer between 2 and 5 items, for instance. And the system can recommend a number of groups. If I want to reorganize these items, for instance, the system can tell me it's best to consider 2 subfolders. We now want to validate this approach. So first we need to assess if these recommendations are useful. It depends on users' preferences. They might not wish to follow the recommendations at all. And semantic constraints. Even if users are okay with the recommendations, they might not be able to follow them. And finally, we need to assess the model accuracy. So to see if the selection time predictions are accurate. And we are also interested to know if there is a top-to-bottom visual ordering for some hierarchies, if we want to validate our heuristic about group ordering. For the first evaluation, we ask participants to modify hierarchies. So, for instance, with this practice example of 8 items with copy, cut, new tab, etc., one possible outcome is the creation of 2 subgroups, file and edit with copy, cut, paste. The interface looked like this. At the top, a legend. In the top right corner, some information about the current structure and the words used in the experiment. With help, there was also the best choice. Here, create 1 new group and transfer 3 nodes. On the left was the interactive tree, and with help, in the bottom right corner, some information from the model. An array with the time prediction gains with different possibilities. And because this array can be quite large, some input fields to query the model. We created 2 datasets of 60 words, each randomly chosen among animals, house items, movies, and famous people. And we considered unequal groups to enforce unbalanced resulting hierarchies. We had 16 participants, and we counterbalanced the pairs system, help, no help, and datasets within participants. And they were instructed to do as they would do on their own without help, and with help to try to follow the recommendations while still considering meaningful grouping. So here is an example. First, a large list of 60 words, the modified hierarchy without help and with help. And if we look closer, we can see that this participant considered group based on the nationality of famous people without help. And with help, the participant considered why they were famous and also the nationality. And results show that recommendations can indeed help users to create theoretically time-efficient hierarchies. And if we look at the number of nodes included in the hierarchy, we can see that they used our model to, of course, create more nodes. And participants reported that they would actually like to have such recommendations for their own files and folders. They found it useful and helpful. But, of course, they also felt that it was slowing them down, and sometimes it was also interfering with their own preferences. Now we know that these recommendations can lead to time-efficient hierarchies, but this time is theoretical, the predicted time, and we need to validate the accuracy of these predictions. So for that, we considered 3 common layouts, linear, radial, and grid. And we had 6 menu instances per layout. And during a session, we started with the calibration of an eye tracker to analyze the visual search. Participants then performed a fixed task to get the pointing time without the visual search, and then the item selection task. We had 21 participants, 7 per layout. So we first need to determine the delay parameters used by the model. So for D1, because our participants were novices, they did not know the items, we considered the novice visual search time, which we indeed found linear with the number of items for the 3 layouts. For D2 and D3, we use the pointing and steering time based on the fixed task, linear with ID, the index of difficulty. So ID was the standard ID for linear and grid layout, and the number of slices for the radial layout according to previous work. Here are the results of the linear regressions. And we can see that for the linear layout, we have a quite smaller R square than what we are used to in HCI. So this can result from approximations we did. We just considered the height of the target, not the width. We didn't apply any adjustment for accuracy, to name a few. But the goal is to validate our model, even if a series of approximations are made along the way. And here are the results for the linear regressions of the actual empirical selection time according to the predicted selection times, with adjusted R squared of 0.91, 93, and 98. So the model can actually be used to compare hierarchy instances between themselves. However, the absolute predictions are not perfect. Otherwise, the linear equations would give us an intercept of 0 and a slope of 1. And this is not the case, and most likely due to our approximations. And finally, regarding the visual ordering, can we define a top and the bottom in these layouts? So for the linear and grid layout, yes, users scan items from top to bottom, left to right. But we did not find any convincing ordering for the radial layout, and definitely not in a clockwise fashion like presented here. So to conclude, we focused on helping end users modifying hierarchies with dynamic content without the need for presupposed knowledge like frequencies, etc. Our model allows to propose a range of solutions for flexibility while still preserving the existing structure and without imposing any constraints on this structure. And we evaluated our approach to validate that the recommendations can actually help creating time-efficient hierarchies, and that these predictions are accurate with 3 different layouts, linear, radial, and grid. So for limitations and future work, first, we need to look into these recommendations in the real world. How to present them first on an OS like Windows or Mac and on smartphone, and also how are they used and do they modify users' behavior on the long run. Also, our predictions are 1 second off compared to empirical selection times. So it might be a coincidence, but 1 second is like in previous work. So this offset might actually be reproducible, so then investigated. And finally, we did not consider any errors. So there is no model for errors. We still don't know if errors are depending on the menu level or not. So right now, we are still thinking about an experimental protocol that would allow us to collect error data without having to wait 3 hours for participants to make enough error data for analysis. Thank you.
Thank you, William, for your nice presentation. We have time for 1 or 2 questions. Is there anyone? Yeah.
I thought this was a mic. Okay, hi, Anirudh Joshi from ID Bombay. So thank you for your presentation. I wanted to ask if there was, if you considered the effect of the frequency of the selected item in your model and how, because so the use case that you presented at the beginning was organizing your movies or your own content in some way. And if you are accessing some particular content more frequently than the others, then, and that might be very individual, so you cannot really make the recommendation based on, without knowing what the frequency is.
Yeah, so we didn't include thank you for the question. Yeah, we didn't include the frequencies in our model because basically it's mostly to reorganize new items, when you add some contents and you want to reorganize your file folders, or your app launchers, you don't know the frequencies. But we still have this heuristic that can be used if the frequencies are known. Let's consider here that the 2 red items are, let's say, twice as likely to be selected than the other items. Then in this case, the model, without adding a new parameters, could consider that these nodes are actually 4 nodes, and then we can still consider it in the grouping. But we didn't want to add an extra parameters in the formula.
Hi, James Egan from Telecom Paris Tech. Did you consider ambiguous or semi-hierarchical structures where, for example, you used the example of movies, where a movie could be an action or a comedy, or it could fit in multiple places in the hierarchy, where the user doesn't necessarily know how to find what they're looking for?
Yeah, and we use that property as a good fact that this is flexible. This is what allows flexibility, for users to actually maybe consider, if the model is telling me to add a few more items in this group I created, I am flexible. These 3 movies could actually be part of this group. We use it as a good property of hierarchy creation.
Okay, thank you, William. We are going to the next presentation.